Till now in my lectures, we have seen how to solve a separable ODE, homogeneous ODE, and exact ODE. Here are some questions for practice. The first question is the value of b that makes in bracket x y square plus b x square y bracket close dx plus bracket x plus y bracket close x square dy is equal to 0. Exact is dash. Please pause the video and try to solve the question. Here mx is the first expression here and nx is the expression here. So we have to find my, that is the del m by del y, and we have to find nx, that is del n by del x. Then we have to equate my with nx. On equating the two, you will get the value of b. The next question is the value of r for which the dE y double derivative plus y derivative minus 6y is equal to 0 has solution of the form y is equal to e raised to rt r dash. Please pause the video and try to solve the question. Here, when we substitute y is equal to e raised to rt in the given differential equation, what you will get is, so e raised to rt will be differentiated twice, so we will get r square e raised to rt. When we differentiate e raised to rt, you get r e raised to rt, and here you simply substitute e raised to rt for y. So you get in bracket r square plus r minus 6 bracket close e raised to rt is equal to 0. Here e raised to rt is not 0 because the exponential function. So we have r square plus r minus 6 is equal to 0, and on solving this quadratic we get r is equal to 2 comma minus 3. The next question is the solution of minus y dx plus bracket x plus square root of xy bracket close dy equal to 0 is dash. Please pause the video and try to solve the question. Here you notice that this equation is a homogeneous equation. Here mxy, that function is a homogeneous of degree 1, and nxy is also homogeneous of degree 1. So by the method that has been illustrated to you of solving homogeneous ODE, you can solve this question. Next question is the solution of y dash is equal to e raised to 3x minus y is dash. Please pause the video and try to solve the question. You must have noticed that this is a linear first order ODE, and you know the method of solving linear first order ODE from your 12th standard. Recall that first you have to find the integrating factor. So for that you transfer that minus y term on the other side. So you have y dash plus y is equal to e raised to 3x. We say px there is the coefficient of y when y is transferred here. So that is px is equal to 1, and qx is this term which is e raised to 3x. So integrating factor is e raised to integral px dx, which will be here e raised to x. So e raised to x is the integrating factor here. So the solution is y multiplied by the integrating factor, that is y ex is equal to integration of this qx times e raised to x dx plus c. You can substitute e raised to 3x in place of qx and solve this integration to get the solution. The next question is, let L be is equal to x square d2 by dx square plus 2x d by dx plus 2 be a differential operator. So this is a linear operator, differential operator. Then L of x cube is dash. Please pause the video and solve the question. So in this case, you substitute x cube here, so you get double derivative of x cube, which is 6x. So 6x multiplied by x square is 6x cube. That is what is mentioned here. Here you take the single derivative of x cube, so you get 3x square. So when 3x square is multiplied with 2x, we get 6x cube, that is mentioned here. And in this place, you simply write 2 times x cube. So that is mentioned here. So when you add this up, we get 14x cube. So L x cube is equal to 14x cube is the answer. Now we proceed on to solving a more classes of ODEs, first order ODEs. So the last thing that we have seen is how to solve an exact ODE. But at times the differential equation, the first order ODE, may not be exact. So we'll see a method of solving such ODEs. Not for all such ODEs, but certain class of such ODEs can be solved. So consider a first order ODE mxy plus nxy dy by dx is equal to 0, which is not exact. So if this is not exact, that would mean that my is not equal to nx. That is, the del m by del y is not equal to del n by del x. So we say that, of course, this is not exact, but maybe when you multiply this with some function, let us say mu xy, multiply this differential equation with a function mu xy, then the equation becomes exact. So something like this mu is a integrating factor. Such a thing, when function which when multiplied to the equation makes the equation exact, such a function mu is called integrating factor. Now suppose such a integrating factor exists, then mu m plus mu n dy by dx equal to 0 will be exact. So if it is exact, then the y derivative of mu dot m, mu multiplied by m, should be equal to x derivative of mu multiplied by n. Simply take the derivative, we get y derivative of mu times m plus mu times y derivative of m is equal to x derivative of mu times n plus mu times x derivative of n. So mu, which is a integrating factor for this ODE, should satisfy the differential equation which you obtain by rearranging these terms. Namely, we bring the mu y and mu x on this side, so it is mu y m minus mu x n plus in bracket my minus nx times bracket close mu is equal to 0. So we get this differential equation. So as I mentioned before, such a function mu is called the integrating factor for the given ordinary differential equation. In practice, if we are looking for such an integrating factor which depends only on one variable x or y, we look for integrating factor which depends only on one variable x or y, because otherwise solving this PD which I kept in the yellow box here will be difficult. So if we assume mu is of any one of the variable x or y, then the solving this equation to obtain the integrating factor is easier. So we consider the case when the integrating factor is a function of x alone. So if it is a function of x alone, taking partial derivative with respect to y will give us 0. So the sum of the term in this differential equation will vanish, will be 0. So it will be easier to solve this differential equation. So as I said, mu we are assuming to be a function of x. So mu is equal to mu x comma mu y, that is the derivative of mu with respect to y, is 0 because it's a function of x alone. So if we substitute this in the given differential equation, we have that the first term is 0 here. So the PD reduces to the following. Now here we bring this n from the left hand side to the denominator on the right hand side. So we get d mu by dx is equal to, in bracket, in the numerator my minus nx divided by n in the denominator, bracket close, mu. So we can solve this differential equation. So given a differential equation, we know the value of whatever term appear in this bracket because we know what is m, we know what is n, and so its partial derivatives we can compute. So the solution of this differential equation can be obtained if we further assume that my minus nx in the numerator divided by n is a function of x alone. Then this differential equation here is only in the variable mu and x. So x is the independent variable and mu is the dependent variable. So this is on the assumption that this particular term is a function of x alone. Then actually the differential equation becomes separable into variables x and mu, and we can solve it. So from this equation you can see that this solution of this differential equation should be in terms of exponential, and clearly the solution is mu x is equal to e raised to integral my minus nx in the numerator divided by n in the denominator dx. Clearly when you differentiate this, this is the differential equation that you get. So here, on assuming two things, namely the integrating factor is a function of x alone, and the fact, and assuming that my minus nx in the numerator divided by n is a function of x alone, on these two assumptions we are able to compute the integrating factor. Similarly, we can have case 2, a very symmetrical case. This was the differential equation which we had obtained in the yellow box in some slides behind. So this differential equation, if we assume that mu is a function of y alone, then again one of the terms gets cancelled, namely partial derivative of mu with respect to x is 0 then, because the function mu is a function of y alone. So what we obtain here is what is mentioned below. We have rearranged, this term is 0, we bring the m to the denominator, and this is what we obtain. Now here again we have already made an assumption that mu is a function of y alone. Now we have to make the assumption that this particular term which appears in the bracket is a function of y alone. So what we have is d mu by dy is equal to nx minus my in the numerator divided by m times mu. In this differential equation, we make another assumption that nx minus my, this term in the numerator, divided by m, this whole thing is a function of y alone. If we assume that, again this differential equation becomes an equation in two variables, namely y and mu, where mu is the dependent variable and y is the independent variable. And this will be in the variable separable form. And again, the solution will be in exponential, and like the case before, here the solution will be mu y is equal to e raised to integral nx minus my divided by m dy. So the integrating factor is very similar in the two cases except for small changes. So here the integration is done with respect to dx, and there is change here, and here we have this integration with respect to dy, and there is a change in this term. So under these two assumptions, namely when mu is a function of y alone and when nx minus my in the numerator divided by m is a function of y alone, we have computed the integrating factor. So we'll see an example where these things occur. So the ordinary differential equation that we are going to treat here is what is given, namely bracket 6 in the bracket 8xy minus 9y square bracket close plus bracket 2x square minus 6xy bracket close dy by dx is equal to 0. So here this is mx and this is ny. Sorry, this is m, namely m is equal to 8xy minus 9y square, and n is 2x square minus 6xy. So we want to compute the integrating factor here because this equation is not exact. So first we compute what is my and then we compute what is nx. The partial derivative is to y and partial derivative with respect to x. So here it is mentioned my is equal to 8x minus 18y, nx is equal to 4x minus 6y. Now we observe that my is not equal to nx, so this is not an exact ODE. So the only hope here is if we have an integrating factor by the methods we have learned. Of course, it can be solved in other methods, namely it is also a homogeneous ODE, but here we want to solve using this integrating factor. So we'll try this method which we have discussed in the previous slide, namely integrating factor depending only on one variable. So in that case, we have to check what is my minus nx divided by n. When you compute that, we get 4x minus 12y divided by 2x bracket x minus 3y. So here we have put the value my minus nx from here and n from here and from here, and you see there is cancellation happening and you get 2 by x. So we see that this term is a function of x alone. Then by our earlier discussion, we can assume that our integrating factor is a function which depends on x alone, and then we have this form: d mu by dx is equal to 2 divided by x times mu. Now we solve this. This is a separable ODE, so you can bring the mu in the denominator here and dx in the numerator here and integrate. We'll get log mod mu is equal to 2 times log mod x, which is same as log of x square. So thus we get ln mod mu is equal to ln x square. We don't need the integration constant here, because anyway this integrating factor is going to be multiplied to the given differential equation to make it exact, and if you assume the constant to be 0, still it works. So we have the integrating factor here, mu x to be equal to x square. So we multiply the given differential equation with this integrating factor. So this differential equation that is mentioned here in blue, multiply this with x square. So it will be 8x square, x cube, sorry, we have now on multiplying x square we have 8x cube y minus 9x square y square plus 2x raised to 4 minus 6x cube y bracket close dy by dx. So that is mentioned here. We can check that this is the exact ODE. We also know from the method that this has to be an exact ODE. You can check if we take this as m and this as n and compute the partial derivative of m with respect to y and partial derivative of n with respect to x, then they are equal. Previously these were not equal. Now this will be equal and this will be an exact ODE, and now we will apply the method of solving ODE. So what we do, whatever is the new mx here that we call ux. You recall this method from the previous lecture. So we call this mx to be equal to ux, and this factor that is appearing here and nxy that we called uy, derivative of u with respect to y. So if this is ux, namely the partial derivative of u with respect to x, then we integrate this. So we integrate ux. That means we have to integrate this term that is appearing here. On integration, clearly we get, what do we get here? We get 2 times x raised to 4y, integrate with respect to x. And then this term, when you integrate, this x square will become x cube divided by 3. So this will become 3x cube y square, and there will be a constant appearing, but the constant will depend on y, because we have integrated only with respect to x, this partial derivative. So we have this uxy to be equal to this term plus ky. Now, as per our method, we have to differentiate this with respect to y and then equate this with this uy that is appearing here. So we first write this, what is appearing here as it is, and then we differentiate the above appearing ux. On differentiating, what we get, we're differentiating this with respect to y. So this will be 2x raised to 4, and this will be 3x cube, and then 2 times y. So that will be minus 6x cube y, and the derivative of ky with respect to y. So this k dash y. So when you equate the term appearing on the left hand side with the term appearing on the extreme right hand side, we get y dash k dash y is equal to 0. So we can say that ky is constant. So when you substitute in our ux that appears here, we get the solution to be equal to 2x raised to 4y minus 3x cube y square is equal to c. So this solution, this implicit solution is a solution of the given ODE. We'll see one more example. Solve the ODE. Minus y plus x dy by dx is equal to 0. This ODE is not an exact ODE. You can check it. Here the mxy is minus y and nxy is x. So when you take the my, you get minus 1, and nx you get 1. So they are not equal. So it is not an exact ODE. So one possibility is to find the integrating factor. So we check what is the value of nx minus my in the numerator divided by m. As we just now checked, here the nx is 1 and my is minus 1. So nx minus my will be 2. So when we divide nx minus my with m, we get minus 2 by y, because m is minus y, which is a function of y alone. So from the previous discussion, we know that we can write d mu by dy is equal to minus 2 by y mu. This differential equation, here we can assume that mu is a function of y alone. Then this is in a form which we know it is a separable ODE, so which depends on the variable mu and y alone. So we can solve this. So we bring the mu on the left hand side in the denominator and take the dy on the right hand side. So what we get is ln mod mu is equal to minus 2 of ln mod y. Now this, when you take this 2 inside, we get ln of y square, and we take the minus inside, we get ln of 1 by y square. So you can write mu y is equal to 1 by y square. We don't write the integration constant here. This is a integrating factor for our differential equation. So we multiply this to our differential equation. What we get is this differential equation, and here you can check that this differential equation is exact. Here the new m is minus 1 by y, because it's y, and we'll cancel with this term here, and the new n is x by y square. You can check that my is equal to nx in this case. And now, of course, you can solve this exact ODE by the method that we know, the long method that we have discussed before, but this can be also be solved by inspection. We know that this particular thing which is appear on the left hand side is the derivative of a very known function, namely it is the derivative of minus x by y square. You can check it, because when you take the derivative of minus x by y, what you do, you square the denominator, and then in the numerator you take the derivative of the numerator, namely x, and write y as it is. So this minus sign, so we get the first term to be minus y dx, and the next term will be put a minus sign, so minus minus becomes plus. Then you take the derivative of the denominator, that is dy, and keep the numerator as it is. So it will be plus x dy. So this is what you get. Then you actually divide it by dx, and this is how it looks like. So what is appearing here is nothing but d of minus x by y, that is equal to 0. So d of this particular function is equal to 0 when that this particular function is constant. So you can absorb the minus sign in the constant. So you have x by y is equal to c. This is the solution of the given differential equation.